Okay. Well, we've kind of completed the previous discussion. And I say here, remember that T consists of columns of eigenvectors. If A, again in formal mathematical language, A ain't got n eigenvectors, where A is presumably n by n, then you can't be diagonalized because ain't no square T. And what I'm saying is, if A is n by n, if you don't have n eigenvectors, you're not going to have n column vectors to put into your T matrix. So T won't be square if you try to do it. So it's not going to work. You have to have a full set of eigenvectors to do a similarity transformation. Okay, now, it turns out I'm going to use the same matrix we did before. I tried to make up a matrix and it turns out it didn't work. So we're going to write the equation y prime equals our matrix times y plus a non-homogeneous vector here. Okay? And again, something beyond you completely understand as a completely valid system. Okay? Now, we're going to make a change of variable. So I referred to this as a change of variable. This is our change of variable, y equals tz. So we've got a new variable z. Now if you're hung up on what z is, well, it's real easy to see that. You don't really need to know this to do what we're saying to do here. You see it at the end. But if y equals tz, then pretty clearly if you multiply both sides by t inverse, you get ty equals z. Our t inverse y equals z. So z is just t inverse y, and that follows immediately from this. But you don't need to know that. Not yet. We'll use that in a minute. So if you don't understand that, put it off. Okay, so all I want to do is replace y with tz. So we replace y with tz. Y prime gets replaced by the quantity tz prime. And y gets replaced by tz. And everything else is the same as it was. Now, of course, T is just a constant matrix, and because of the rules of differentiation of matrices and so forth, this derivative is just T times z prime. The constant matrix just comes out of the derivative. Okay, and that's the only change I've made between this step and this one. But now I'm going to do something. Okay, I'm going to multiply every term in this matrix by T inverse. Well, I'm going to write that out. I'm going to write T inverse Tz prime equals T inverse, and my red circle kind of obliterated, or at least hit a bit of that inverse. This is T inverse times this plus T inverse times this. Okay, well that's simple enough. In the first place, we can calculate T inverse times this, which I did over here. I didn't have room to write it all out, but here's what you get. You get, and got smudged here a little bit. If you multiply T inverse by this, I'll read it to you. You get e to the 2t divided by 2. That's not the 2 t's divided by 2. The whole blame e to the 2 t's divided by 2. And minus e to the 3t divided by 4 minus 1/4. And then something very similar, e to the 2t divided by 2, but it's plus e to the 3t divided by 4 plus 1/4. And if you just do the multiplication, and take the T inverse matrix, multiply it by this, well, again, I've written most of it out here, but I didn't have room to write it clearly. And it's not all that clear here. It will be on the next board. Okay. Well, then what else can we do? Well, T inverse times T is just the identity, because T inverse is the inverse of T, and the identity times Z prime is just Z prime. So T inverse T times Z prime just gives you Z prime. Okay? And T inverse times our matrix times T, we just group it that way, is just what? Well, T inverse times this matrix 3, 1 times T, we just calculated it up here. It's our diagonal matrix with the eigenvectors times Z. So Z prime is this times Z plus this thing that we get from doing T inverse times our non-homogeneous part. Okay, well, where does that take us? Well, you're going to love it, okay? We'll see that in the next clip.